Hello everyone, welcome to my channel. In today's session we are going to see the primal dual relationship problems. Okay, so any linear programming problem, it can be either a maximization problem or minimization problem, can be stated in another equivalent form, okay, based on the same data. So the new linear programming problem will be called as dual, or you can call it as a dual linear programming problem. So in general, it is immaterial which of these two problem is called. Okay, so it can be called as a primal or dual, but remember one thing, the dual of dual is always a primal problem. So let us see now. Let us take down this problem. Okay, the problem is given here: max z equals x1 plus 2 x2 plus x3, subjected to three types of constraints. So the problem is in primal now. Now we have to find another equivalent form using the same data. That will be the dual form for the given primal LPP. Okay, and also you can see that the table is shown here. So any primal problem, if you get, if the problem is of type minimization, then we have to convert that first into the canonical form and verify that whenever you have any minimization problem, make sure all the inequality should be in a greater than or equal to symbol. If it is not there, we have to convert that into greater than or equal to. Then we have to convert that into the duality. Okay, for the dual problem, all the minimization problem will be maximization, and every symbol should be less than or equal to. Similarly, for maximization problem, the canonical form, what we need to verify is we have to convert all the inequalities into the less than or equal to symbol, and then after doing that, we will convert that back into the duality theory. The maximization problem will become minimization, and all the less than or equal to symbol will become greater than or equal. Okay, so I'll explain the algorithm with the help of this problem here. Okay, so let me first convert the given problem into the canonical. So as I already told you, the canonical form for the given problem will be so first I will write canonical form. Okay, so the canonical form. So what I will do means the canonical form, that's a maximization. So maximization will remain as it is, right? So I'll write max z equals, okay, this will be same, the objective function x1 plus 2 x2 plus x3. Now when I see for subjected to constraints, I should see that what are the inequalities here. So as I told you, for the canonical form of maximization problem, everything should be less than or equal to, but in our case the first and third constraints are satisfying, but not the second constraint. So this second constraint has to be converted into less than or equal to. To do that, all the signs will get interchanged, right? So now we'll write the entire three constraints into the canonical form for the given problem. So it will become 2x1 plus x2 minus x3 less than or equal to 2. This remains same, but here, so we will write 2x1, so plus x2 becomes minus x2, minus 5x3 will become plus 5x3, and greater than or equal to become less than or equal to, minus 6 will become 6. Okay, and the third concept will remain as it is, that's 4x1 plus x2 plus x3 less than or equal to 6, and all the non-negativity conditions whatever we have, that is x1 and x1 comma x2 comma x3 all are greater than or equal to 0. Now the same canonical form we will write it in a duality theory. Okay, so what is the dual form of this? So the dual form will be, so the dual form will be minimization, right? So in place of z I will write w. Okay, so you can see that in the above table whichever I had given. So maximization, I wrote it everything, I made everything to the less than or equal to. Now I'm going to convert it to minimization, but by symbol should be always greater than or equal to. So I write min w equals, that's w is a new variable, okay, here. So what I will do means, here every constraint, well, the RHS value will be considered as the number of variables. Okay, so constraint, number of constraints will be given as number of variables, and number of variables will be given as number of constraints here. So how many constraints we have? We have 3 constraints. That means we have 3 new variables that we will label it as w1, w2 and w3. So our objective function will be with respect to the RHS value here. Okay, so you can see here how I'm going to write it here. So min w equals 2w1 plus 6w2 plus 6w3. that is this RHS value, 2w1 plus 6w2 plus 6w3, okay, which are subjected to constraints, Now we have to take column by column. You can see here 2, 2, 4. So it will be written as 2w1 plus 2w2 plus 4w3, and what should be the symbol? Greater than or equal. So I should write greater than or equal to, you have to consider the objective function values, greater than or equal to 1. Second constraint will be 1w1 minus w2 plus w3 greater than or equal to 2. Similarly, third constraint will be minus w1 plus 5w2 plus w3 greater than or equal to 1. This is the way we need to write. So let us write that now. Okay, so min w will become 2w1 plus 2w2 plus 4w3 greater than or equal to 1. Second constraint will be w1 minus w2 plus w3 greater than or equal to 2. Third one, minus w1 plus 5w2 plus w3 greater than or equal to 1, and w1 comma w2 comma w3 all are greater than or equal to 0. So this is the dual form of the given primal solution. So if you take a dual of this dual, you will get the same primal problem again. Okay, so dual of dual is always a primal problem. So this is the first problem for you. Okay, now we'll solve another problem. So this is the first problem. Now we'll take another problem. Okay, so let me consider the second problem as minimization. Let us solve the minimization problem. Okay, so I'll write it as minimize z equals 2x2 plus 5x3, okay, which are subjected to constraints x1 plus x2 greater than or equal to 2, 2x1 plus x2 plus 6x3 less than or equal to 6, then x1 minus x2 plus 3x3 equal to 4. Okay, when I write equal to, it means it is unrestricted, okay, to the inequalities, and then I write x1 comma x2 comma x3 all are greater than or equal to 0. So this is the primal problem in minimization. Now first of all we have to convert this into canonical form, right? So we will write the canonical form of the given primal problem. So what will be the canonical form? So this will be minimization only. Min z is equal to 2x2 plus 5x3. Okay, then it will be subjected to constraints, and now we have to verify everything should be what? If it is a minimization problem, everything should be greater than or equal to. Now first constraint is satisfied but not the second and third one. So what I will do means, first I will write the first constraint as it is. So that is x1 plus x2 greater than or equal to 2. Okay, but when it comes to the second constraint, it is not satisfied, so we have to convert that into greater than or equal to. When doing that, we know that signs will get interchanged. So this will become minus 2x1 minus x2 minus 6x3 greater than or equal to minus 6. But what about the third constraints? In the third constraint it is written x1 minus x2 plus 3x3 equal to 4. Now the same thing can be rewritten as, so for example this can be here, this can be rewritten in two ways, like x1 minus x2 plus 3x3, either I can write it as less than or equal to 4, okay, and I can write it as x1 minus x2 plus 3x3 greater than or equal to 4 in two ways. Okay, so again let me convert that into canonical form. So the first equation will be what? It is less than or equal to, so I want greater than or equal to, right? So this one I'm talking about here. This is the first one, this is the second one. So first one will we have the less than or equal to symbol, so we'll convert into greater than or equal to. So it will become minus x1 plus x2, right, minus 3x3 greater than or equal to minus 4, and last one will remain as it is, x1 minus x2 plus 3x3 greater than or equal to 4. So this is your canonical form. Now you have to convert this into the duality form. Okay, now let us write the dual form of this. So what is the dual form now? So what is the dual form here? So minimization, right? So minimization will convert into the maximization, right? So I'll write maximize z, or I can write it as maximize w. So I will write it as maximize w, which is equal to now, which will be equal to what we have to check right here, right? So it is here, all the constants will be considered as the number of variables in the objective. So it will be 2w1, all these RHS value we are going to write it in the objective function, but in place of x1, x2, x3 we will write it as w1, w2, w3, w4, because now you see actually you had only two variables right here. Now you will have four variables. Okay, four variables, and since we had four constants, that four constants will be converted into only two constants. That is called we interchange. Constants will become variables, and variables will become constraints. So let us write down now what is the max w now. 2w1 minus 6w2 plus 4w3 minus 4w4. Okay, right? So we can also interchange this also. Okay, minus 4w3 plus 4w4, that also you can write it as. And then we are subjected to constraints. Yeah, first we have to take first column. Okay, that will be with respect to the second column will be respected to 5. So let us write that. So it is subjected to constraints what? w1 minus 2w2 plus w3 minus w4. Okay, so that is what maximization. It should be always less than or equal to. Okay, that we have to write it here, but we can see that we don't have x1 here. So what we will write? Less than or equal to 0. Okay, and another one that is w1 minus w2 minus w3 plus w4. Okay, that will be less than or equal to 2. We are going to write. Okay, and the third constraints. Okay, here we had only two variables, but since there was no x1, so the first constraint I am writing with respect to x1 here. This is for x2 and next is for x3. Okay, so x3 will be what now? w1 is not there, so I will not write it. Okay, so I'll directly write from the w2, that is minus 6w2 plus 3w3 minus 3w4, and that is less than or equal to 5. Okay, this is the way we need to write, and we'll make and w1 comma w2 comma w3 comma w4 all are greater than or equal to 0. Okay, this is how we can write. Now what we can do, we can see that there are some common terms here, w3 w4, okay, right, and here also w3 w4. So we can here also w3 3w3 minus 3w4. So what we will do means we will rearrange here, we will rearrange w3 minus w4 as w3 dash, okay, and we'll substitute in all the constraints as well as in the main objective function, because here also we have w3 minus w4. So how will you rewrite the entire dual form now with respect to that? So I'll write it as max z is equal to 2w1 minus 6w2 plus 4w3 dash, correct? No, w3 minus w4 is w3 dash, which is subjected to constraints w1 minus 2w2 plus w3 dash less than or equal to 0. Here it will be w1 minus w2 minus w3 dash less than or equal to 2, and this will be minus 6w2 plus 3w3 dash, right, and this is less than or equal to 5. So when I do that, this w1 and w2 will be greater than or equal to 0, but w3 dash will be always unrestricted, okay. So we'll write and w1 comma w2 both are greater than or equal to 0, and w3 dash is unrestricted, that will be unrestricted, because you see that in the third constraint, okay, in the third constraints as per the question we got equal to 4 here, okay. That's the reason we are writing that third variable w3 dash will be unrestricted, right. So similarly we can consider some other problems also. So I will solve one more problem on maximization, okay, maximization. So let us take down the problem here. So the problem is max set. This is another kind of problem, okay. The problem is max set equals 16x1 plus 14x2, okay, plus 36x3 plus 6x4, which are subjected to constraints 14x1 plus 4x2 plus 14x3 plus 8x4 equal to 21, okay, equality condition. Then we have 13x1 plus 17x2, okay, plus 80x3 plus 2x4 less than or equal to 48, and x1 comma x2 are greater than or equal to 0, and they say that x3 comma x4 to unrestricted, okay. That means the fourth and third and fourth variable to be unrestricted. So this is the problem, primal problem. Now we have to convert this first into canonical problem, okay. Let us convert that into canonical form. So when you are going to convert into canonical form, so we have to remember here, what is that we need to remember? That equal to symbol can be written in two ways, less than or equal to into greater than or equal to, and the second constant will be less than or equal to only, okay. Canonical form means maximization, everything should be less than or equal to. That is what we need to do, okay. So let us first write the first constraint, that will be first constraint, we'll write max z equal to 16x1 plus 14x2 plus 36x3 plus 6x4, okay. These are subjected to constraints, So let us write the first constraint, that is 14x1 plus 4x2 plus 14x3 plus 8x4 less than or equal to 21. Another 14x1 plus 4x2 plus 14x3 plus 8x4 greater than or equal to 21. Then 13x1 plus 17x2 plus 80x3 plus 2x4, that should be less than or equal to 48. Okay, now first one is okay, last one is okay, but the second one is not okay, right? So what shall we do it here? So we'll write it here. So this can be rewritten as minus 14x1, right, minus 4x2 minus 14x3 minus 8x4 less than or equal to minus 21. So this is your canonical form. Okay, this is your canonical form, and now we are going to convert this into duality form. Okay, we'll write the dual form of this. So what is the dual form? Maximization becomes minimization, right? So here I will write dual form. Maximization becomes minimization, min w equal to, okay, so RHS, you see the value 21w1 minus, so second will be minus, right, minus 21w2 plus 48w3, correct? So subjected to constraints, what will be the next? 14w1, look at the column, second row, first column will be minus 14w2 plus 13w3, okay, and it should be greater than or equal to what? 16. See the value here, 16. Okay, similarly 4w1, write the next one, 4w1 minus 4w2 plus 17w3 greater than or equal to 14. Okay, next will be 14w1 minus 14w2 plus 80w3 greater than or equal to 36. The last one is 8w1 minus 8w2 plus 2w3 greater than or equal to 6. Okay, now we have to rearrange, because we know that the w1 minus w2 we can make it as w1 dash, right? So these are common here, you can see these are common, so this we can make it as w1 dash, and we can make the next w3, and that we can make it as w2. So we'll rearrange here, we rearrange w1 minus w2 equal to w1 dash, and we'll make w3 as w2. Now the final form will be what? The final dual form will be min z equals, or min w equals 21w1 dash, correct, plus 48w2, w3 will be replaced as w2, okay, which are subjected to constraints 14w1 dash plus 13w2, right, greater than or equal to 16. Similarly 4w1 dash plus 17w2 greater than or equal to 14. Then comes 14w1 dash plus 80w2 greater than or equal to 36. Then finally 8w1 dash plus 2w2. Yeah, now guys, there is a small change here. As you can see here, as per the question, as per the question, the third and fourth variable should be unrestricted. So in the sense, now what we are going to do is, the third constraint, third and fourth variables are unrestricted, right? That means when you convert into dual, the third and fourth constraint should be unrestricted. That means there should not be any greater than or equal to, nor less than or equal to. So what we need to do, this greater than or equal to what we are written, no, this we need to change, guys. Okay, so I will rewrite this entire equation as 14 W1 dash here. Okay, I'll rewrite this entire equation as 14 W1 dash plus 80 W2 equal to 36, because the third fourth constraint should be unrestricted. Okay, it should be 36, and finally 8W1 plus 2W2 equal to 6 here. Okay, and finally what will you write? W1 dash is unrestricted, comma, W2 should be always greater than or equal to 0. So this is your final duality theory or dual form of the given primal LPP. Okay, so we have solved totally 3 problems. Okay, so if you have any queries regarding to these problems, please drop your comments in the comment section below. Thank you so much for watching.